In this hour, we will talk about the controllable decomposition of an LTI system, which is necessary in order to study the stabilizability of the system. Okay. So to motivate, therefore, the controllable decomposition, let's first try to understand in a sort of informal way what we mean by stabilizability, okay, over a second order numerical example. Okay, consider the following LTI system. Okay, consider x dot equals 0, 1, 6, minus 1x plus 1, 2, u. Okay, so this is our A matrix and this here is our B matrix. So let's answer some simple questions regarding this system. First of all, is this system stable in the sense of Lyapunov? Okay. For that, all we have to do is we have to check the eigenvalues of the A matrix. So let's do that. Si minus A determinant is S minus 1 minus 6 S plus 1. Okay, and that's S plus 1 minus 6, and that reads S plus 3 and S minus 2. Okay, so we have an eigenvalue. Both eigenvalues are real. One is at minus 3, the other is at plus 2. Because of that second eigenvalue, which is positive and real, we claim, we see directly that this system is not stable in the sense of Lyapunov. Okay, lambda 2 equals 2, which is positive, hence this system is unstable. Okay. Now let's also have a look at its controllability properties. In other words, is this system controllable? Okay. For that, what we do is, well, there are many ways we can check controllability, but since it's a second order system, it seems simplest to form the controllability matrix. Okay, B will be one of its columns and AB will be the second column, and then we can check whether that matrix is full rank or not. Okay, so the controllability matrix B AB. So since the input is scalar, the controllability matrix will be square. So BAB reads, B is 1, 2, and AB reads 2, 4. Okay, and for controllability, we require that the rank of this matrix equals the order of the system, which is 2. Now we see clearly that the columns are linearly dependent. Okay, we have 1, 2, and we have 2, 4. One is a scaled version of the other. Therefore, the rank of this matrix is 1, which is strictly less than the order of the system. Hence, the system is not controllable. Okay. So, rank of controlled matrix does not equal the order of the system 2. Therefore, this system is not only unstable, but also turned out to be uncontrollable. Okay. Now, still, let's try to answer the following question. Now, this system is unstable, and with some proper control input, possibly with state feedback, we want to stabilize the origin. Okay, so we want every solution to converge to the origin. Okay, so that's what we desire. Now, but the system is not controllable. Therefore, it's not for certain that whether we can achieve our goal or not. Okay, but still, it's an important question that's worth considering. So let's continue with that then. Can we still stabilize the system with some feedback law, okay, with u equals minus kx, okay, with state feedback. Okay. Now, it may not be easy to determine or to answer that question at this point, but since the system is quite simple, it's just second order, therefore we can give it a shot at it. So let's try to, what we can do is we can try to figure out the eigenvalue locations of the closed loop and figure out the dependence of those eigenvalue locations on the parameters of our feedback law, K. And then perhaps we can answer this question here. So x that equals ax plus bu. Okay, so that's our system. This is our A and this is our B. And now what we want is we want to drive the system under some feedback. Okay, that is u equals minus kx. Now u is a scalar, x is a vector in R2, therefore this feedback law should be a row vector, okay, or a matrix of dimension 1 by 2, so that kx produces a scalar. Okay, so that's our feedback law structure, under which the closed loop system becomes x dot equals ax minus bkx, and then that we can write as x that equals some matrix times x, and that some matrix is called the closed loop system matrix. Okay, so we have a minus bk times x. So this is our closed loop system matrix. Okay, and what we want is we want to determine whether by choosing some proper feedback law K, can we make the eigenvalues of this closed loop system matrix A minus bk all with negative real parts. Okay, and K is a 1 by 2 matrix, or in open form it's it has this structure. Okay, K1 is its first entry and K2, both scalar real, is its second entry. Okay, so let's plug in that structure for K, and we have A and B form the closed loop system matrix, which will be depending on K1 and K2. From that closed loop system matrix, we can figure out the characteristic polynomial, and then we can perhaps talk about the pole locations, eigenvalue locations, through the characteristic polynomial, which will be in terms of K1 and K2. Okay, so the question that we want to answer, which is directly related to the stability of the closed loop system, is that eigenvalues of the closed loop system. Okay, now let's try to talk about that a little. Okay, the closed loop system matrix equals A minus bk. Okay, so A was 0, 1, 6, minus 1. Okay, this is our B, and here we have our K matrix with entries K1 and K2. Okay, that equals 0, 6, 1, minus 1, minus K1, K2, and then 2 times that, 2K2. Okay, and that produces the following closed loop system matrix in terms of the feedback law, K1 and K2. Minus K1, okay, 1 minus K2, 6 minus 2K2, 1 and minus 1 minus 2k2. Okay, so that's our closed loop system matrix. Let's figure out the characteristic polynomial corresponding to this. Okay, Si minus a closed loop is S plus k1, S minus 1 plus k2, 2k1 minus 6, and S plus 1 plus 2k2. Okay, and now we have to compute the determinant of this, which reads S squared plus k1 plus 2k2 plus 1s and 3k1 plus 6k2 minus 6. Okay, so this is the characteristic polynomial of the closed loop system matrix. Okay, now here we have the coefficient of the first order term, which is a linear function of the feedback parameters k1 and k2. And likewise, this is the coefficient of the zeroth order term. And it seems that by choosing k1 and k2 properly, we can make these two things whatever we want. And we can make the whole polynomial whatever we want. So that means we can place the eigenvalues wherever we want of the closed loop system. But it's not the case, because this can be written as the following: S plus k1 plus 2k2 minus 2. Okay, so no matter how you play with k1 and k2, you will never be able to move the eigenvalue at minus 3. So this eigenvalue of minus 3, remember that that's an eigenvalue of the open loop system of this A matrix. So you cannot move it anywhere by state feedback law, and that has to do with the fact that the system is uncontrollable. So it looks, so that sounds a little bad, but there's one good thing about it. And the thing that's good about it is that even though we cannot play with this eigenvalue, note that it's at minus 3, therefore it's a stable eigenvalue, okay? And we can play with the second eigenvalue, we can put it anywhere we want. So if we place the second eigenvalue also on the open left half plane, then both eigenvalues of the closed loop system matrix will be on the open left half plane, and as a result, the closed loop system will be exponentially stable. In other words, all the solutions will converge exponentially to the origin. Okay, so therefore, even though the system is unstable and uncontrollable, we can still, by choosing a proper state feedback, we can still stabilize this system. Okay, so this is S plus 3, nothing can be done about this. About this eigenvalue, and it has to do with the uncontrollability of the system. And here we can place lambda 2 closed loop, second eigenvalue of the closed loop system, wherever we want, okay, as we wish. Okay, now let's continue and finish our design by choosing a proper feedback law. Okay, so let's choose for instance, the feedback law as 1, 1. So both K1 and K2, we choose to equal 1. So here we have 1, here we have 2. 1, 2, 3 minus 2, that produces 1. So what we have therefore as the characteristic polynomial of the closed loop system, S plus 3 times S plus 1. Okay, so S I minus a closed loop becomes s plus 3 times s plus 1. Both eigenvalues are now on the open left half plane. So, lambda 1 closed loop, okay, the first eigenvalue of the closed loop system also equals the first eigenvalue of the open loop system, because we cannot play with that eigenvalue. So that's at minus 3. And that has to do with the fact that the system is uncontrollable. This is at minus 3. And as for the second eigenvalue, okay, of the closed loop system, it's at minus 1 if you choose your feedback law as 1, 1, okay. And as a result, all the eigenvalues of the closed loop system are on the open left half plane, and we have exponential stability in the sense of the upper, okay, exponential stability. Okay, now this simple example carries some important lessons which we will formalize, which we will generalize into the concept of stabilizability. Okay, so let's write that down. Even though the pair AB is uncontrollable, we can still make state converge to the origin, and converge to the origin in exponential fashion as time goes on, okay, as t goes to infinity. Such pair AB is called stabilizable. Okay. So, if the system is controllable, then by definition we can make the state converge to the origin. Okay, there's no problem with that. But this example has shown us that even if the system is uncontrollable, then there's still hope that we can make the state converge to the origin, perhaps not in finite time, but eventually, okay, if certain conditions are met, okay, and such pair, okay, for which all the solutions can be made converge to the origin is called a stabilizable pair, or such system is called a stabilizable system. Okay, now we will eventually provide a systematic definition, a formal definition for stabilizability, but that requires us to introduce the controllable decomposition first. Okay. So let's therefore talk a little bit about that controllable decomposition. Okay. Okay, now we consider the general case. Consider the systems of the same order. System 1, x that equals ax plus bu. X is in Rn and u is in Rk. And here is our second system, whose state is denoted by a different notation, z that equals a tilde, z plus b tilde u. We have the same input, z is in Rn. Okay, now suppose that these two systems are algebraically equivalent. Okay, suppose that system 1 and system 2 are algebraically equivalent, by which we mean by a proper similarity transformation, we can move from one representation to the other. Okay, that is, there exists a similarity transformation or a change of coordinates matrix okay, they all mean the same thing. A matrix that's invertible, Rn by n, where z is related to x through this identity. Okay, z equals t inverse x, or x equals t times z, such that we have the following relation between the respective matrices. A tilde is T inverse AT and B tilde is T inverse times B. Okay? And now our eventual aim is such that we're going to figure out some T using the controllability properties or uncontrollability properties of a given system, such that after that transformation, the new representation allows us to see certain things in a clearer light. Okay? But now let's compare the controllability of these two systems, which are algebraically equivalent to one another. Okay, and here is the claim, which is not that surprising. Okay, system 1 is controllable if and only if the other system is. System 2 is controllable. Okay? In other words, controllability is invariant under similarity transformation. So let's see why that claim has to be true. Here is a simple proof in which we use the controllability matrix. Okay, so let us construct the controllability matrices for both of these systems. So the controllability matrix of the first system is denoted by C, and it's B, AB, A square B up to the n minus first power of A. Okay, A n minus 1 times B. Now this C matrix has n rows and n times k columns. And we know from our earlier lectures that the system is controllable if and only if the rank of this matrix is n, or the rows of that matrix are linearly independent. Okay, how about the controllability matrix of this new system, the Z system? Let's form that also. We have the same structure, B tilde, A tilde, B tilde, A tilde n minus 1 times B tilde. Okay. Now, in order to be able to compare those two matrices, let's remember what A tilde and B tilde were in terms of our the original system parameters A, B, and our similarity transformation T. Okay. So that can be written as B tilde was T inverse B, and then we have A tilde, which was T inverse A T times B tilde, which is T inverse B, and so on. T inverse A T n minus 1 times T inverse B. Okay, so that's our C tilde. Note that here we have T and T inverse They make identity, therefore we can remove that. And this second term we can write as T inverse A times B. For the third term, we're going to have this square times T inverse B, but this square can be written as T inverse times A square times T. Okay? Why? T inverse A T square is T inverse A T times T inverse A T. This T and that T inverse, they will cancel, and what we have is T inverse A T. T inverse A square T. So clearly, this is true for any power of A. Okay? And that allows us to write the following. T inverse B, T inverse AB, T inverse A raised to the power n minus 1 B. Okay? So where we use the fact that T inverse A T kth power equals T inverse A K T for any power K. Okay. Note that in this case all the matrices are multiplied from left by T inverse, and that can be written as follows. The T inverse can be taken outside the brackets, and we can write T inverse times B AB A n minus 1B. And once that's done, we immediately recognize that the contributive matrix of the first system, of the original system, appears. And we have, therefore, T inverse C, okay, for our C tilde. And because of that, since T inverse is a non-singular matrix, the rank of C tilde must equal the rank of C. Okay, so the number of linearly independent rows of C tilde must equal the number of linearly independent rows of C. So that means that if the rank of this C tilde is n, then and only n, the rank of C controllability matrix is n, and by the relation between the rank of the controllability matrix and controllability, we see that this claim holds true. Okay. Okay. So then rank C tilde equals rank T inverse C, and that equals rank of C, because T inverse is an invertible square matrix. Okay. Okay. And finally, we can write system 1 controllable if and only if rank C equals the order of the system. So this result we already know. And rank C equals n if and only if rank of C tilde is n. Okay, and rank of C tilde is n if and only if the system 2 is controllable. Okay, as a result, just remove the intermediate steps. System 1 is controllable if and only if system 2 is controllable. Okay. Furthermore, even though for the uncontrollable case, the rank of C tilde and C, okay, they are equal. And remember that the range space of the controllable matrix gave us the controllable subspace. Okay, so even though for the uncontrollable case, even though the controllable subspace for system 1 and controllable subspace for system 2 would be different subspaces in general, there will be something same about those two subspaces, and it would be their dimension. Okay, because that dimension equals the rank of the controllable matrix, and we know that the rank of both C and C tilde, they are the same. Okay, now with the help of this claim, we're now ready to figure out the similarity transformation the proper similarity transformation, which will take us from an arbitrary system to its controllable decomposition representation. Okay. So this is the end of our proof. Now, for the system x that equals ax plus bu, we will construct the so-called controllable decomposition. Okay, and the reason that we're constructing controllable decomposition is because through that we will study the stabilizability. We will define and then study the stabilizability property of a system, okay, which is a more general or a relaxed version of the concept of controllability. Okay. So we begin by introducing the following notation. Let SC be the controllable subspace of the system x that equals ax plus b, or the pair AB, okay, which we know from our earlier studies equals the range space of the controllability matrix, okay. Be the controllable subspace. And we let n bar be the dimension of the subspace. Okay, now that dimension of the subspace can be at most n. N is the order of our system. Okay, A is n by n. If n bar equals n, then by definition the system is controllable. Okay, but we're considering the general case where system is allowed to be uncontrollable. In that situation, we have to introduce a new notation for the dimension of the controllable subspace. Okay, and that's n bar. N bar is the dimension of the controllable subspace, which equals clearly the rank of the controllability matrix C. Okay. The following observations will be useful. One of them is that the controllable subspace is invariant under A. Okay, is invariant under A. Why is that true? Remember that SC is range space of C. In other words, controllable subspace is spanned by the columns of C. Okay, and columns of C are here, B, A, B, and so on. And due to the Cayley-Hamilton theorem, okay, since any matrix, for any square matrix, its nth or larger power, n being the size of our matrix is n by n, its nth or larger power can be written as linear combination of powers from 0 to n minus 1, and the zeroth power of a matrix is the identity matrix by definition. Because of that, the Cayley-Hamilton theorem, plus that when constructing the controllability matrix, we go as far as the n minus first power of A, the controllable subspace must be invariant under A. That is, pick a vector from controllable subspace, multiply that vector by A, okay, A times V. The new vector that you obtain can still be written as a linear combination of the columns of the controllability matrix. In other words, that new vector must also belong to the controllable subspace. The second observation, which is much simpler, is that the range space of B, okay, must be a subset of the controllable subspace. Okay, the controllable subspace can be any vector in controllable subspace can be written as a linear combination of the columns of the C matrix, and the first k columns are the columns of B, Therefore, clearly, the controllable subspace contains the subspace that you obtain by considering the range space of the matrix B. Okay, so those were simple observations. Okay, now how to construct this T, which will give us the so-called controllable decomposition. So let V be a matrix that has n bar columns, okay, and each column is a vector in Rn. Okay, so V is an n by n bar matrix, and that matrix is such that its columns make a basis for the controllable subspace. Since the dimension of the controllable subspace is n bar, such a matrix exists. Okay, in fact there are many such matrices. We just pick an arbitrary one. Okay, B such that its columns form a basis. Okay, so by definition they are linearly independent for the controllable subspace, which we denote by S sub C. Okay. Now by our invariance observation that's made here, we can find a square matrix, let's call it AC, okay, of size n bar by n bar being the dimension of our controllable subspace, such that A V equals V times AC. Okay, now why is that? Why such a matrix exists? Pick, let's say, the first column of V. First column of V, since the columns of V make a basis for controllable subspace, the first column of V belongs to the controllable subspace. Now we multiply that column by A. Since controllable subspace is invariant under A, that new vector that you obtain, A times the first column of V, must belong to the controllable subspace, which is spanned by V. Therefore, that new vector can be written as a linear combination of the columns of V. When you write that linear combination, collect all the coefficients that appear, stack them in a vector which will be of size n bar, and that vector will be the first column of AC. Then move on to second column, do the same thing, and so on. So such a matrix AC must exist due to invariance plus the fact that V, the columns of V make a basis for controllable subspace. Okay. Furthermore, since the range space of B, or the which is subspace spanned by the columns of B, is necessarily a subset of the controllable subspace, we can find the matrix which we denote by BC R n bar by K, and K is the number of columns that B has, satisfying B equals what? V times BC. Okay, first column of B, okay, belongs to SC, therefore it can be written as a linear combination of the columns of V. Write it as a linear combination, collect the coefficients, okay, stack stack those coefficients into a vector, and that's the first column of your BC, that vector of size n bar, and do it for the second column of B, and so on. That's how we construct BC. Okay. Now we're almost ready to propose a transformation T, which will take us from x that equals ax plus bu to the controllable decomposition. Now, if n bar equals n, in other words, if the system is controllable, then let the transformation be equal to V. In that case, V becomes n by n, and it's a non-singular matrix. Therefore, we can take our transformation matrix to equal V. Okay. In fact, since this is just an arbitrary basis, and for this case, the controllable subspace is the entire space Rn, we can take V to be the identity matrix. If V is the identity matrix, or T is the identity matrix, then that means after the transformation, you still obtain the same system. In other words, that system is already in controllable decomposition. Okay? But that's not interesting. The interesting part is when n bar is strictly less than n. Otherwise, let U be a matrix with n rows and n minus n bar columns, such that its columns together with the columns of V span the entire space Rn. Okay, so what we do basically is we start with V, and V, if V has n bar columns, but if V has less than n columns, so what we do is we complete that basis to be a basis for the entire space Rn. So for that we have to add n minus n bar more columns to V. Okay. Spar Rn, and with that U we defined finally our transformation matrix, and define T as this matrix where the first n bar columns come from the columns of V, and the remaining n minus n bar columns they come from the columns of U. This is a square matrix, and since together they make a basis for Rn, clearly this T must be invertible. Okay. Note that T inverse exists. Okay, now we're going to operate on our system with that similar transformation and see what we get. Okay, we now proceed as follows. A times the similarity matrix T equals A times V and U. Okay, this is how we constructed T, and that reads AV and AU. Okay, and that reads, okay, let me put it here, and that reads excuse me, that reads, okay, now we're going to use this thing here, AV equals VAC, and write VAC here, And here, for this AU, we write identity times AU, and identity we can write as T times T inverse. Okay, so we can write T inverse AU. Okay, AV equals VAC, and here we did this just at this point useless thing that instead of introduced an identity matrix here, and we wrote identity as T times T inverse. Okay, and that can be written as following. This VAC equals VU matrix times, okay, AC 0 matrix. Okay, V times AC plus U times 0. U times 0 is 0, so that produces VAC. And here we still have T inverse AU. Note that this VU is no other than T. So here we have T times something, and here again we have T times something, therefore we can take that T outside the brackets. And that allows us to write the following: T times AC 0, and we have here T inverse AU. Okay, now let's work a little bit on T inverse AU term. So what we do is we partition that matrix as follows. Okay, so let us partition T inverse AU as, first of all, this is an n by n minus n bar matrix. Okay, so we're gonna partition it as the following: A12 and AU. Okay, now this new matrix must have n minus n bar columns, and this term is such that that block is n bar by n minus n bar, and which makes the bottom term to be a square matrix of size n minus n bar by n minus n bar. So this is n minus n bar by n minus n bar matrix. Okay, then we have AT equals T times this, and now we write T inverse AU in this form, and we reached the form that we want, an upper block triangular form for A tilde 0 AU. Okay, furthermore, we can write B equals VBC. So this we already observed earlier, and now that can be written as VU times BC and the 0 matrix, where BC is n bar by K, and this 0 matrix is n minus n bar by K. Okay, VBC plus U times 0 gives us VBC, which is B. Therefore B we can write as, note that this is our T matrix, T times this matrix, and this new matrix will be our B tilde, and that equals T times BC 0. Okay, so let's summarize what we have obtained. Okay, from these expressions we can eventually write AC0 A12 AU is T inverse AT, and T is chosen in a way that it equals V and U. It has two pieces, V and U, and V is such that the columns make a basis for the controllable subspace, and U is just an arbitrary set of columns such that together they make a basis for the entire space, or in other words, together they make this matrix invertible. Okay, and this special B tilde is, or has this form, BC0, which can be written as T inverse times B. And this thing is called the controllable decomposition for a given pair AB. Okay. In the next hour, we will study some of its important properties.